Initiated. Yes, there it comes. And we'll go from the current slide. Okay. Only announcement I know for certain about. I'm sure there's some more out there that I don't know for certain about, but I do know for sure about is that tomorrow morning, normally I'm on the Birmingham campus, 8 to 12, office hours. But tomorrow I've got an appointment right across the road here at the street here at UAB West, an eye appointment at 8:15. Now I'm hoping it'll be over by 9:15. I don't know how reasonable I hope that is, and if so, I think I can be back to the Birmingham campus by 10. Maybe before 10, it may be after 10, but sometime around there I hope to be able to be back at the Birmingham campus. So don't go looking for me between 8 and 10. I probably won't be there. If you do want to check, go on and call the number, but don't leave a message. You have the Friday number, which is 929-6409. Don't leave a message because that's not my phone. You know, I can't access the messages from there. So you can check and see if I'm there. You can also check with the secretary, Ms. Rose Saxon, 929-6377. If you can't catch me, you can find out if she's heard anything. All right, good deal. Any questions on anything we've covered so far, administratively or algebraically? All right, now where we left off last time, we had done example 3 and example 4, but example 5, 4, and 5 were not in the on the PowerPoint show, so we're doing those separately. So let me get my pen set up. Okay. Now, here's what example 5 is. Sketch the graph of, I'm going to write it up here, f of x is equal to, oh boy, this looks like a good one, minus 9/2, one of my favorite coefficients of all time, x, okay, and here's Quinn. Okay? All right. Example 5, top of page 129, section 2.2, chapter 2, polynomial rational functions. We're doing polynomials now, 2.2, rational polynomial functions of higher degree, and here is the one we're to sketch now. F of x is equal to minus 9/2 x plus 6x squared minus 2x cubed. Okay. How would you begin this problem? Anybody? What's the messiest thing about the problem that you see? I know what most of you will say, but there is something messier. It's a little bizarre about it. Okay, yeah, you know y'all are going to focus in on the fraction, and that is messy, I admit that, but what's a little more significant to solving the problem? I mean, you can start it now, any way you want to. What's it? Someone say something? Anybody? Patel's here, he'll say something, and I know that somebody in Deja will, so let me gotta find you. There's Samaya. There's Patel. And there's Radeja. Okay. All right. Chapter 2, polynomials. That's what we're doing now in rational functions. 2.2 polynomial functions of higher degree. Example 5 on page 129. This one right up here. We already acknowledge that it's a little messy that you do have a fraction as a coefficient. Okay? We can see if we can live with that. What else is messy about this? Second? Not in standard form. Excellent. And how would you put it in standard form?
Negative 2x.
Okay, start with the highest order, negative 2x cubed plus 6x squared minus 9 over 2x. Very good. Good first step. Okay, now that you've got it more in a standard form, what could you do next? And you could have done this next step first, but it's okay. I like it doing it this way. What would you do next?
Take common.
Second?
Take common.
Okay, common factors out, and what would that be?
Minus 2x.
Okay, I don't see a 9 halves x in the other two terms. I see an x in all three terms, but leave the 9 halves there for now. So let's factor out, but I would also want to factor out the minus. Maybe you said that. Let's factor out a minus x. What does that leave us with in the first term? 2x. Anything else? Squared. Next. Minus 6x plus 9 halves. All right. Good job. Okay. What's the next thing you would do? I don't think there's a lot of hope in factoring this, is there? Because how many things these things can you put together with 9 halves is, a factor of 9 halves. That's going to be tough. So what can we do with that? Now, what it said to do is sketch the graph. And you could just randomly start plugging in numbers. That's certainly I can't remember which one, but likes to say, what is it? Do a table. I believe that's Dion. So do a table. And that is a legitimate way to proceed. It's a little hard and maybe a little messy at times. But let's see. I probably should have done this first. Either at this step or that step, we can say something about this function. Second? What is? What's going down? Okay? Okay, let's look at this one. Okay? Now the leading coefficient, sure enough, I can't mark you present with the ionizing pen, so I'll have to use the other one. Okay. Leon's here. And Tara's here. Okay, anyone else come in while I wasn't looking? Or even while I was looking but didn't notice you? Okay. Okay. You said going down, I'll agree with that halfway. Okay? But it's not completely going down the tubes. No, I mean, what can you tell me about this? Say again? Okay, the leading coefficient's odd. The whole function is odd, but the leading term is odd, which means it's going which way? Say again? Okay. The whole function isn't odd because it has an even coefficient here. So the whole function isn't odd, but the leading term is. That does tell us something. What does that tell us? Especially about the end behavior. What does that tell us? If it's an odd, if n is odd, the leading exponent is odd, what does that tell us about end behavior? Say again? I can't hear. Okay? We can do, that's what we're trying to do here. We have one x-intercept. If you want to do that now, we certainly can. What is an x-intercept? Anyone know that? If f is equal to 0, the function is equal to 0, set that equal to 0, you can tell me 1, 0 right now. X is equal to 0. Okay? So X 0, Y 0. Guess what, team? That's also the Y-intercept. Put X equals 0, you get Y is equal to 0. So sure enough, 0, 0 is it's two intercepts. It's the X and the Y-intercept. Okay? So let me go back and erase this for now because I don't quite want that yet. But I'm really fishing here for what does the degree of the polynomial tell you about end behavior. An odd degree says what? Second? Okay. Yeah, he's already said that. That would be if the whole function were odd. This is not odd. It has an even component in it. It's a neither function. Ah, very good. The end behavior is going in opposite directions because that's odd. If that was even, it'd be up and down, or down and down. But because it's odd, they're going in opposite directions. Now, can you tell me which direction they're heading? Which? Which is which? I know if they're opposite directions, one down, one up. Okay, I got that. Okay. Noted. Which again?
First is going down.
What you mean by first?
Minus 2x cubed.
Okay. We're talking about large X is negative or large X is positive. One of those is going up, one's going down.
Negative.
It's going what?
Yeah.
Really? Notice this. The sign of the leading coefficient flips them. Normally you'd be right. That would be. A negative X would be going downhill. But with a minus in front, that flips it to go uphill. A positive X would be going uphill, right? Except when you put the negative, it flips it down. So they're going in the opposite directions. So negative X is going up, and positive X is going down. There's our end behavior. We could have done that, should have done it, either at this step or that step, because that's what we're doing. Graphing the function, this tells us something about the function. And we've got our one x-intercept anyway. Okay. But we're kind of stuck, aren't we? Okay. We got our end behavior. We've got one intercept. We know being a polynomial function, not going to be any asymptotes. Okay. So, we're stuck with trying to do something with that. What kind of an expression is that? Okay. I know you're in here. You can't hide. Amina, right? Huh? Huh? A little louder. Oh, TR. Right, I'm sorry. Okay. You're hiding too, aren't you? There you got it. Okay. And Krista and somebody else. Oh, Carla did. Okay. There you are. Anyone else come in? Oh, I wasn't looking or tied up or whatever. Loose me. No, okay. All right, we're trying to graph this function. Alpha of x equals minus 9 blah, blah, blah. Okay? Two things we've done. We put it in standard form, which is decreasing order of the powers. Three things we've done. We factored out the greatest common factor, which is just a negative x. And we identified that was an x-intercept. And we identified, so it's probably four things we've done now, that the end behavior is up to negative, down on the positive side. Okay? Now, we're stuck with what to do with that. What kind of an expression is this? Quadratic expression. Now, one thing we could do is get this in its standard form. And how would we do that? I'm going to leave that minus x alone here. What's the first step to get this in standard form? Factor what? Okay, 2, yeah, well, just 2. 2, the A term, okay? 2 out of the first 2 terms, the x terms. What would that leave us with? X squared minus 3x blank. Remember that ugly blank? Okay. And then we have a plus 9/2 out here. Remember that? Okay. Now what's the next step we do to get it in standard form? The linear term by 2. That will give us a minus 3/2. Now, as soon as we do that, all right, there you are, H. Okay, anyone else come in since the call roll? Okay, as soon as we take half of that, what we can do down here, I like to do this because it keeps me from forgetting to do it. Down here, it's going to be an x. Half of that is minus 3/2. I already know what this is going to look like. Oh, here they are. Morning. Okay. Okay. Got the Harmons here. Anyone else come in since the call roll? Okay. This is example 5, top of page 129, section 2.2. Okay. Now, I just did that part because I knew that's what it's going to look like at the end. It's not ready there yet. What else to do? As soon as you take half of this, minus 3/2, then we do what to it? Square it. Now, what is the square of minus 3/2? Positive 9/4. So we're going to add this here. 9/4. However, and I forgot something here. Let me put that in too close too soon. Okay. Okay. However, as soon as you add that here, you've changed the whole problem. What did you do? Goodness gracious, this is hard to tell. Since we got the bracket here, don't look out there. Okay, just stay inside the bracket. You got a 2 times 9/4, which is?
4, 5, 4.2.
Whew, goodness gracious. This new math is getting to me. Okay. All right. 18/4 is the same as 9/2. We just added 9/2 to the side, didn't we? Or to inside here. So we need to subtract 9/2 there. Look at that. There goes our fraction. Oh no, we were beginning to love our fraction. Okay. We're going to subtract 9/2 there. Okay. And that just leaves us with this. Okay? Now, I'm beginning to regret doing this because this is part of a bigger problem. And this doesn't give us anything like a 0, which is what we need. This gives us a vertex of a parabola, but this is part of a bigger problem, so that's not really what we're looking for, is it? Sorry about that. It seemed like such a good idea. Say again? Can't hear. Yeah, I'm right. It's not a good idea. Thanks. Okay, right. Okay. I thought, you're right. It's not a very good idea. Okay. All right. Yuck. Okay. It will help us plot some points, though. We can say that. For instance, when x is equal to, we already know what it is when x equals 0. When x is equal to, let's go, let me set up my, I don't need that many tick marks, but I'm going to put them in. These are not very even, okay? We can go one or the other, right or left from this. One place, it's a weird thing to do. Let's set x equal to 3/2. So x equals 3/2, we're going to be right about there, 1.5. Okay? Now, what would this become? X equals 3/2. 0. Okay? And so that does give you. Okay? Then this becomes 0, and that's 0. So we have another x-intercept. We're right. There is some good to do of this. The reason for that is the k is 0. Okay? So it turned out being a better idea than I thought. Okay? Oh, Hamina decided to show today. That's good. All right. Good deal. All right. Good to have you. We're doing example 5 on page 129, section 2.2. Okay? So we found another 0. Yes. Okay? Now, you know what? Don't think we're going to come up with another 0 anywhere, because I can't think of, oh my goodness, the more they come, the worse. Okay, never mind. Okay. All right. DB didn't make it, right? Huh? Okay, he's waiting till the very last. Okay, we got that. Okay. All right. Never mind. Dylan made it. Okay. Gray made it. Brandon made it. And Q made it. All the baseball folks came. Okay. Oh, well, you weren't in that one. Okay. All right. Anyone else come in since the called roll? Okay. All right. We're doing example 5, top of page 129 or near the top in section 2.2. Okay. It was a weird-looking function written not in standard form, so the first thing we did was write it in standard form. Once we got it there, we looked at end behavior, or not quite, but we did. And because it's a minus here, an odd here, it's going up on the minus end, down on the positive end. Okay? Then we factored out what we could, which was a minus x. So that gave us, someone noted, that also gave us our x and y intercept, 0, 0, because with x equals 0, y is equal to 0, and vice versa. Then we couldn't do much with this, so we decided to do our standard form of a quadratic expression. And when we did that, we found that k went away, so the h turned out being a 0. It doesn't usually, but it did in this case. So that did help a little bit. Now, how many zeros would we expect to have? 3, okay? Now, we only wound up with 2, okay? Now, that would work okay, and I think it will, because this one might wind up being a double 0, wouldn't it? Because this is squared, right? So, I believe we do have all our zeros, and DB even showed up. Okay. All right. Okay. Now, this is a double 0 because it's x minus 3/2 squared. That's a factor here. Okay? So, right now, since it says sketch, I think we can sketch this. What does a double 0 tell you? Multiplicity of 2, as opposed to multiplicity of 1, which usually is a multiplicity, but yeah, I still count it that way. What's going to happen here? What's the function going to be doing at that 0? Crossing the x-axis. What's it going to be doing at this 0? Touching it but not crossing. Kissing it and going back in the same direction, right? Okay. We have enough to do at least the graph here. We know this has to be coming from very positive, so it's going to have to cross here. It couldn't be crossing anywhere else because you don't have any more zeros. So it has to cross there. Then it comes up and kisses the axis here and goes back down and winds up going downhill. So we got it. we have a decent sketch of this right now, okay? I'm going to just guess that it's coming down like this, crossing there, turns and makes a U-turn, it's called a change of direction, and touches here, and then goes back down here. Now, I don't know if that's exactly right. If I wanted it exact, what could I do? Or more exact? What y'all love taking? Test points. A test. Okay. All right. You could choose x equal -1 and see what that turns out to be. It's not hard to do. You all have calculators. You could do that. You could choose x equal 1, see what that turns out to be. And then you could even do x equal 2 and see what that turns out to be. And then you could get a more precise, but I bet you anything, -1 is going to be up there somewhere, +1 is not going to be very far down here, and 2 could be anywhere down there. Anyone want to do that quickly, just to see what those values are? Y'all are way too lazy, aren't you? Okay, I could tell. Okay. Anyone want to? Okay. You happy with that? Let's see how the book, oh, look at that. Looks like the book got it right too. Okay? And they did choose 3 test points. Now, why did they choose -1/2? I'm not sure. I would have chosen -1. Why did they choose +1/2? I'm not sure. I would have used +1. That's much easier. And by the way, +1 is very easy. Just go to the function either here or here and put a 1 in for every x. So then you just add your coefficients. Okay? It'd be 6 minus 4.5, right? This is 4.5, 6.5, so that's -1/2. At x equal 1, you're at -1/2. Look at that, folks. Can you get much closer than that? Okay? So at x equal 1, this is going to be -1/2. Whew. Lucky. Skill. Okay. Now, -1 wouldn't be a lot harder. This would become a -1. That would be a +2. This would be a +6, because that stays a +1. So 2 + 6 is 8. Then you add 4.5. That'd be 12.5. Whoa, it's way up there somewhere. So yeah, well off scale. Okay. 2 would be just a little harder. That would be 8. That would be -16 plus 24. That's going to be +8. But then we have a -9. That's a -1. So it would be right here. Oh, look at that. I think that's right. Okay. Now, this one was off a little bit. That should be a +12, but I was off scale there. So that's not a bad rendition, is it? Say it's great. No, never mind. Okay. We won't go there. There is a checkpoint at the bottom of the page. Since y'all were so responsive on this one, I would say a checkpoint would be a good thing to practice on. Don't you think? All right, let's move on. That was too much fun. Okay. Now we're at the intermediate value theorem. Okay. Okay. The intermediate value theorem implies that if f of a, which is pick an x value of a, plug it into the function, you get f of a. So this is your xy pair, right? And b, pick another x value, b, plug that into the function, f of b, that gives you your y for that b. If these are 2 points on the graph of a polynomial function, now here's the requirement. F of a cannot be the same as f of b. Okay? The intermediate value function theorem doesn't tell you anything if those two are equal. But if they're not equal, and most of the time they won't be equal, okay? Only rarely will they be exactly the same. Then for any number d that's in between f of a and f of b, or f of a and f of b, any number in between those two, for any number d, there must be at least one number c between a and b where that happens. And that would be f of c would be equal to d. Now, why is that true? Remember, these are polynomial functions. Give me 2 features of a polynomial function. 1 is all I really need, but I always like to say them together. Two features of a polynomial function. Think jazz. Never mind, y'all don't think jazz. Smooth and continuous. Two features of a polynomial function. They're always smooth, always continuous. Right now, we're only interested in the continuous part. Because if f of a is down here, and f of b is up here, a being here and b being there, there is some place where a d in between f of a and f of b, for any number in there, there's got to be at least one place, c down here between a and b, such that f of c is equal to d. Why? Because it's a continuous function. You can't get from here to there without going through every point in between the two. Now, you may go several times. I mean, this polynomial function could have done this. You know, as long as it was smooth and continuous, it could have crossed d 3 or 4 times. But it has to cross at least once. Does that make sense? Continuous function, there's no way around it. There's no gaps, no holes. There has to be, for every value in between f of a and f of b, every d value in there, there's going to be at least one c between a and b, such that f of c is equal to d. A lot of blah, blah, blahs there. So what's the point? You said you knew that, didn't you? Okay. Let's see if they give you the point. Yes. So here's the intermediate value theorem stated. Let a and b be any real number such that a is less than b. Okay? If f is a polynomial function, as soon as you read that, you know it's what two features? Smooth and continuous, especially continuous. Such that f of a is not equal to f of b. See, if f of a equal to f of b, there's no guarantee there's going to be a value, well, there's nothing in between f of a and f of b. So it's sort of a moot point there, okay? So if f is a polynomial function such that f of a is not equal to f of b, then on the interval a to b, f takes on every value between f of a and f of b. At least once, maybe more than one time. So the intermediate value theorem helps you locate real zeros of a polynomial function. Here's how. If that x equal a, tell me, you want that to be, you want the function to be positive or negative there? I don't care. Pick one. Positive. So at x equal a, the function is going to be positive. Now, if at x equal b, it happens to be negative, guess what? You're going to have at least one crossing of the x-axis. At least 1 0. May have more than one, but you're going to have at least one. So if you can find the value x of a, which the polynomial function say is positive, you chose the same thing the book did, and another value x equal b, in which it's negative, you know, you can conclude without a doubt the function has at least one real zero between those two values. Intermediate value theorem. Okay. And they give you one here. Here's a function. F of x equal x cubed plus x squared plus 1. Okay? Now forget what they're saying here. Give me an x, any old x. 1. Okay? If you plug in a 1 there, what do you get for f? 3. Very good. Positive, right? Give me another x. 0. Plug it in. What do you get? 1. Still positive. Give me another x. 2. Guess what? Anything bigger you get is going uphill fast. So going larger, not going to work. But if you go negative, give me a negative value. -1, is that what you said? Okay, that would be a -1 plus 1. That's still positive, isn't it? Get further left. -2. What would this be? -8 plus 4 plus 1? -3. So I know we have to have a 0 between x equal -1, which was positive, and x equal -2, which was negative. Ha! And that's what they say too. This is negative when x equal -2, positive when it's x equal -1. So you know you got to have a 0 in there. Okay? There's not a single tool we've used so far that's going to tell us where that 0 is. Okay? But we know it's there somewhere between -2 and -1. There's got to be a 0. Okay? Now, looking at the graph can suggest it may be a little closer to -1 than -2, but it's hard to say, especially if you draw graphs like I do. Never mind. Okay. So, what can you do from here? By continuing this line of reasoning, you can approximate any real zeros of polynomial functions to any desired accuracy you get. Okay? And example 6 is going to do that. Okay? And that's what we're going to next. And guess what function they're going to use? Oh, it's a different one, isn't it? But pretty close. Okay? So let's approximate. They say the real zero. We'll get to why that's true later. But let's find a real zero. So what will you need to do first? Well, cheerleader, give me a x. Give me an x. Second, what'd you say? Anybody. They're not hard to pick. Second? 2. Okay? If you give me a 2, this will be 8 minus 4. That's going to be 4 plus 1 is 5. So that's going to be positive. Give me another x. -2. This will be -8 minus 4, because -2 squared is still positive 4. So -8, -4, -12 plus 1, -11. Sure, we found some, but they're pretty far apart. Let's try to get them a little closer. Y'all don't do the easiest ones. Y'all are way too hard working. You need to be a little lazier. What's the easiest x you could give me? 0. All right, now you're thinking. Okay. That would be what? 1. Okay? Now, I have a feeling if you go too far this way, it's just going to get bigger and bigger and bigger. So let's head that way. What's just on that side of 0? -1, what would this be? -1. -1, that'd be -2 plus 1 is? -1. So here, at 0 it's plus 1, at -1 it's -1. We found a bracket, okay? So f of 0 is equal to 1, and f of -1 is equal to, what did we say that was? -1. Okay, I thought we said. Okay? So we know it's got to be in between. Pick a number between 0 and -1. Say again? -1/2, right? -1/2. So let's try f of -1/2. It almost sounds like time for a calculator to me. That's going to be a -1/8. I can do this on my head. -1/8 minus 1/4. Right? Does everybody follow this? Plus 1. Well, that's going to be -3/4 plus 1, which is going to be positive 3/8. Positive 5/8. So there it's positive. What does this tell us? The zero's in between -1/2 and -1, doesn't it? Okay? Pick a number between, I'm going to go to decimal, so I'll make it a little bit easier. Between -1 and -0.5. Number between -1 and -0.5. Because you got to go between the positives, and positive and negative. Negative what? 0.6. -0.6. Okay, let's try that. F of -0.6. Okay? Cube that. You would have to choose that one there. Pull out your calculators. Okay, 0.6, -0.6 cubed. Okay, now that time be sure your -0.6 is what you're cubing. Not in front of it, but -0.6. It's going to be negative. So what's that going to be? -0.6 cubed. It can't be that hard, okay? Negative point what?
216.
216. All right, good. And then minus a 0.6 squared, which would be minus 0.36. And then we're going to add a 1 to it. Okay? Now, I don't know what that's going to come out to be, but it's still going to be positive because these two add to something like 0.62 plus 1. That's going to be positive 0.38 or something like that. So, let's go between 0.6 and negative 0.6 and negative 1. Give me another decimal number between negative 0.6 and negative 1. Anyone will do. There's lots of them to choose from. 0.7. Okay. He's going up by increments. That's fine. Okay. Now, pull out the calculator. Negative 0.7 cubed is going to be minus 0.343. Second? 343. Thank you. Okay. Then we're going to have a minus 0.49. I can do that one. Okay. And then we're going to do a plus 1. Okay. Guess what? We're still positive, aren't we? Because those two add to be 0.8 something another. Okay. 833. So give me a number between negative 0.7 and negative 1. 0.8. I thought he might say that. Okay. All right. And negative 0.8 cubed is negative 0. Second? 512. This time I think we're going to make it, folks. This will be negative 0.64. Yep. That's greater than, actually less than negative 1. When you add it to plus 1, that's going to give you something negative. So now we stuck between negative 0.7 and negative 0.8. Not negative 0.75. And you can just keep the process going until you get so close you say, hey, that's close enough. Okay? In the very, very, very old days, there was a great mathematician named Archimedes. This was way back, BC, way back BC. And he, really clever guy, but no one knew how to get the area of a circle. They knew how to get the area of polyhedrons, in other words, figures, triangles, squares, those kinds of things. So what he did, he took a square, he took a circle that he was trying to estimate the area, took a square that put on the outside of the circle, and a square that was inside the circle, calculated those two squares, areas, and then averaged it over, gave him a pretty good number. But he was real sharp. He could then take a pentagon and put one outside the circle and one inside the circle, do those two areas, take the average, and get it even closer. And then he could do hexagons, he could do septagons, he could do octagons. I mean, he kept getting shapes closer and closer to the circle. There one on the outside, one on the inside. It was really rigorous math. I mean, goodness gracious, figuring the area of those things, you could do it, but it's really tough. But he did it. And he finally said, this is close enough. You know what he called that method? The method of exhaustion. Okay, he said, okay, I'm tired of doing it. Let's stop there. So you can do this as long as you want to. This is going to get you within 0.2. Okay, you can keep going as much as you want to. After a while, you can get within 0.02. And at some point, you say, hey, that's close enough. That'll be my 0. Okay, so that's one way you can do this. Intermediate value theorem gives it to you. Now, what they show in the text, let me erase my scratch here, and let's see how they did it, and see if we came up to anything close. Okay? Begin by computing a few function values. They started at -2 and got -11, I think. Did we do that one? I don't remember if we did. We did, okay. We got -1 was -1, 0 was 1, 1 was 1. Hey! Here we have a change of sign here. We know it's got to be between 0 and -1. We learned that, didn't we? Okay? So, because negative 1, f of negative 1 is negative and f of 0 is positive, you can apply the intermediate value theorem, conclude there has to be a real 0 between negative 1 and 0. To pinpoint this, then just pick something in between. They went right to 0.8, negative 0.8 was a negative 0.152, I think we got that, and f of negative 0.7 was negative 167. Hey, no, positive 0.167. So we know it's between negative 0.87 and 0.8. Hey, we learned that too, didn't we? Okay? And so it has to be between the two. And sure enough, if you graph this thing, of course, how do you do that if you don't have the points? You see it's somewhere out there between negative 0.7 and 0.8. What I would do, rather than just say that, let's take an average of the two and say it's about 0.75, negative 0.75. Not exact, but it's going to be closer than either one of them. Okay? So, here's how that looks. Notice this only has 1, 0. It could have up to how many? 3, but it only has 1. How many turning points should it have? 2. There's a turning point. There's another turning point. So it has the right number of turning points, but the trouble is this one doesn't dip down low enough to give you 2 more zeros. So that's why you can live with just 1. How did you know it had to have 1? How did you know that function right there had to have 1 0? What's that? Okay, I think you're right on the money with that one. The leading coefficient, leading term is odd, which means it's either going to go like that or like that. If it goes like that, it's got to cross 0 somewhere. At least one place, and sure enough it did. End behavior was negative here, positive there. That's not turning back again. Can't have more than 2 turning points. All right, good deal. Make sense? All right. For a more accurate approximation, compute the function between f of negative 0.8 and negative 0.7. Apply the intermediate theorem again and again and again. If you get positive, negative, go between them. Positive, positive, go the other way. Yeah. Keep going. And by continuing the process, you can approximate the 0 to any desired accuracy you choose, or until you get tired. Okay, whichever comes first, which I think will be getting tired. Okay. And that's it. There is a checkpoint, so please do that. It seems like that might be fun. And then there's a summary, and then vocabulary. Let's do the vocabulary. The graph of a polynomial function is blank, which means the graph has no breaks, no holes, no gaps. Continuous. Perfect. Number 2, the blank, blank, blank is used to determine the left hand and the right hand behavior of the graph of the polynomial function. I really don't like their term. If you turn back 1 page to the summary, number 2 on the summary. Oh, you don't have your books. What does it say? The blank, blank, blank. The summary. Summarize. Number 2. 1 page before. Page 131. Leading coefficient test. I like to call it the leading term test. The term gives you more information than just the coefficient. But either one will do. Okay? That's the end behavior. Okay? We've done it at least twice today. A polynomial function of degree n has at most how many real zeros? N. And at most how many turning points? N minus 1. Perfect. Number 4. When x equal a is a 0 of a polynomial function, the 3 statements below are true. X equal a is a blank of the polynomial equation, f of x equals 0. Solution, okay, would be the one way to say it. You could also, I wouldn't say 0 because I use 0 above, so that's a solution of that polynomial equation. Number B, blank is a factor of the polynomial f of x. X minus a, perfect. And C, a0 is an blank of the graph of f. Yes, an x-intercept, to be specific. Okay? Number 5. When a real number, x equal a, of a polynomial function, f, is of even multiplicity, the graph of f blanks the x-axis. We just did one like it a short while ago. At x equal a. No, if it's even, it touches it but doesn't cross. And when it is odd multiplicity, the graph of f crosses the x-axis at x equal a. Very good. Number 6, a factor x minus a to the kth power, if k is greater than 1, yields a blank blank x equal a of blank k. Okay? What's the first two blanks? When k is greater than 1 and you have a factor x minus a to the kth power, this is called a repeated zero. Exactly. Repeated zero, x equal a, and a blank k. What do we call k? Multiplicity. Okay, very good. You're good at charades, right? Okay, good deal. All right. Number 7. A polynomial function is written in blank form when its terms are written in descending order of the exponents from left to right. Standard form. Perfect. Okay, number 8. The blank blank theorem states that if f is a polynomial function such that f of a is not equal to f of b, then in the interval a to b, f takes on every value between f of a and f of b. Intermediate value theorem. Excellent. Okay. Now I think you can do all 9 through 14. That's just matching up the functions with their graphs. However, in the back of the book and at calcchat.com, you'll only find the odd answers, but I think you can do them all. And then do any of the odds 15, either 15 or 17. There's 4 parts to each one, no, 6 parts to 17. You can do either one of those. They're both at CalcChat, 17's at CalcView. You can do any of the odds 19 to 27. They're all at CalcChat, 21's at CalcView. You can do either 29 or 31. They're both at CalcChat. You can do any of the odds 33 to 47. They're all at CalcChat, 43's at CalcView. You can use technology. I think you can do it without it, but give it a shot anyway. Either 49 or 51. They're both at CalcChat. Even if you don't have the technology, you can look at those answers. Then you can do any of the odds 53 to 61. They're all at CalcChat. 59's at CalcView. That's pretty interesting. We didn't do any like that, so if you have any problems with it, be sure to ask on those. Any of the odds 63 to 69, they're all at CalcChat. 67's at CalcView. Any of the odds 71 to 83, they're all at CalcChat. 73's at CalcView. That says technology again, but I think you can do a lot of this without it. 85 or 87, they're both at CalcChat. You can do either 89 or 91. They're both at CalcChat, and 89's at CalcView. And then some applied problems. Do any of the odds 93 through 97. Okay? At least 2 of those are revenue problems. If any of you are going into business, volume problem, that would be fun for anybody. Okay, true, false. There are either 99 or 101. Both of those should be at CalcChat, as the earlier ones were too. And then there's some modeling polynomials, 103, graphical reasoning, 105, and you can think about doing 107 if you choose. They all should be at CalcChat. Any questions? 2.2. Okay. That was a fun section, wasn't it? Say yes. Okay. Hey, I didn't say grunt. Okay. All right. Let's move on to 2.3. We're making pretty good progress today. Okay. What is strike through? I don't know. Okay. Let's set up the slideshow for a current slide and pick up from here. Okay, chapter 2 is still polynomial and rational functions. We're still in the polynomial part. We're now going to do polynomials and how they relate to synthetic division. Does anyone remember what synthetic division is? Yay, nay, or not sure, huh? Okay. So what I think we'll probably do is start off with long division. Yes, that's right. The first objective, use long division to divide polynomials by other polynomials. We love our long division, don't we? Yes. Then we'll use polynomial division to divide certain polynomials, any polynomial by a binomial that's written in this form. Now, I'll go over what my shorthand for this form is later. And then we'll use the remainder theorem and the factor theorem to tell us all sorts of good information about the function. Okay? Now, this is the last section we're going to do before the quiz, so I'll try to have the quiz ready for you on Tuesday. So expect that. Okay, let's start with long division of polynomials. Okay, I'm going to start with long division of numbers because I know that ever since you owned a calculator, you've never done long division again in your life, have you? Admit it, okay? We need to know how to do it, okay? Now, here's a number. 6, oh, let me get my pen set up. Okay, 6, 1, 9, 1, 6, 4. That looks like a really good number. Okay? And let's divide that by the number 12. Oh, where did it go? What in the world happened to it? Okay, let's do it again. It didn't like this number. 619,164 divided by 12. Anyone know what that is right off the top of your head? We probably have to divide. Get your hands off that calculator. Okay, let's do long division. Now, long division is different from adding, subtracting, and multiplying multiplying by one way. All those others, you start at the right and work your way left, right? Start at the lowest digits and work your way up. Division, though, you go the other way. So what would you look at first here?
61.
12 into 61, exactly. How many times will 12 go into 61? 5 times. So you first divide, then you do what? Multiply, okay. 5 times 12 is 60. Then you do what? Okay, and do what? Bring down. Oh, y'all remember this, don't you? Okay, then you divide again. 12 into 19. Now, if 12 wouldn't go into 19 if you brought this down, you put a placeholder there, a 0. But it will go into it. So how many times will 12 go into 19? 1 time. Then you do what? Multiply. That gives you 12. And then you subtract. That gives you 7. And then you bring down the 1. Okay? Now you go do what again? Divide. 12 will go into 71. 5. Almost 6, but not quite, so it's going to go 5. Oh, and by the way, when you do your subtraction here, like you got 1, one thing you ought to do, make sure the 1 is less than 12. It is. And the 7, that's less than 12. It is. If this ever, not when you bring this down, but if your subtraction ever comes out greater than that, bump it up a notch, because it would go into it one more time. Remember? Okay. Whoa! It keeps losing. Okay, 5 times 12 is, we already know that, 60. And then subtract. Oh, I should have asked you that. What you do next? 11. And then you do what? Oh, and you look at that and say, is 11 less than 12? Just barely, but it is, so keep going. Then you do what? Bring down the 6. And then you do what? 12 into 1, 16. 9 times. Okay? And then you do what? Multiply. 108. Okay, this is getting tiring, isn't it? And then what? Subtract, and you get 8. And 8 is less than 12, so you keep going. 4. 7. And then that multiplies with 84. Then you know it went exactly into that. Right? Exactly. What does that tell you? among other things, that 12 is a factor of that because you wound up with 0 remaining. 12 is a factor of that big old number there. And also 51,597 is a factor of that number as well. So we know a couple things about it. We could break this down into simpler factors. I'm not even going to try that one. But anyway, those are things you know. If you had a remainder, what would you do? You put the remainder over that, and that would be, if they had a remainder of 5, you'd say, and 5/12, right? You put remainder over divisor. Remember that? Hey, y'all are good. Y'all are really good at this. So what we're going to do now is, say we have this function here, f of x is equal 6x cubed minus 19x squared plus 16x minus 4, and they put it on a graphing calculator, shame on them, okay, and they look, and it says, we can tell for certain, or very likely, you have a 0 at 2, 0. You have an intercept there at 2, 0. Okay? Over here, I can't tell if that just touches the x-axis or is 2 different values. It looks like 2 different values, but I can't tell what is what. They're too close together, right? And they're in between the numbers, so I just have to make a guess at it. Okay? But because it looks like it does have a 0 at x equal 2, what we can do is divide the factor. If that is a 0 at x equal 2, that means x minus 2 is a factor, doesn't it? So we're going to divide x minus 2 into that. So let's go back here, clear out our chicken scratch here, and do it. X minus 2 will go into, 6x cubed minus 19x squared plus 16x minus 4. Whoa. Okay. Now, how do you think we're going to proceed? Think we may start down here? No, we start over here. And we start with the first terms, right? X will go into 6x cubed how many times? 6x squared times. Somebody remembers their synthetic division, don't they? And then what do we do next? Multiply. 6x squared times x is 6x cubed. You know it's got to be that. We did that. But you also do this one. 6x squared times minus 2 is minus 12x squared, right? Okay. And then what are you going to do? Okay, very good. Okay. You need to subtract, but man, when you've got signed numbers, it's so easy to make mistakes subtracting signed numbers. So what I like to do is change signs and add. That's what you're supposed to do anyway, right? So let's change that to a minus and that to a plus and add them, right? So what do you get? These add to 0. Yes, that's what we wanted to. What does these add to? Minus 7x squared, and then guess what we're going to do? Bring down a plus 16x. Just like we did before, we brought down the next digit. Okay? And here's the other thing. We look at this and say, this degree is greater than that degree, so we keep dividing. Just like if that remainder was greater than this, divide again. Okay? So we're going to keep dividing. Okay? So how many times will x go into minus 7x squared? Minus 7x times. All right? And then what do we do? Multiply. Minus 7x times x is minus 7x squared. That's good. And then minus 7 times minus 7x times minus 2 is plus 14x. Okay? Now I'm going to change signs and add. The sad part is I have to erase that minus to make it plus to make it a minus here. Okay? So I'm going to add now. You could have just subtracted that because that would have been easy. This adds to 0. This adds to 2x. Don't forget the x. And then what do we do? Bring down the minus 4. Okay? Now, what do you do next? And still, you look at this and say, is the degree here less than the degree there? No, it's not. Keep dividing. it goes into it plus 2 times. Okay? And then you what? Multiply. 2 times x is 2x. 2 times minus 2 is minus 4. Ding, ding, ding. Look at that. We knew that, or we thought that anyway, that x equal 2 was a 0, so x minus 2 had better been a factor. As soon as we see a 0 remainder here, we know it was a factor. All right. Okay? Now, what we were doing, okay, was just long division. Okay? But why were we doing that? We were doing it to see if we could figure out what those other 2 zeros were. Well, guess what? If this thing was equal to 0 at x equal 2, okay, then this thing will be 0 at those other zeros as well. So let's now set this equal to, let's throw my pen around, okay, and get it all tangled up in a knot here, okay. Okay, this is strange. Okay, got it. All right. And can we do this? Can we factor this? If you set it equal to 0, how would we solve that? Try factoring. Okay? So let's see if we can factor that. Okay? What's one possible factorization for 6x squared? There's several of them. What's one? Say it? 3x times 2x? Is that what you said? Okay, that sounds like a good one to me. And then, where do we look next? We look at the sign of the last term as a positive. What does that tell you about these two signs? They've got to be the same, and since this one's negative, they both got to be negative. Very good. Y'all are quick. Okay? Now, we look at possible factorizations of 2. There's only one. 2 and 1. Let's try that. Y'all are lucky. Okay? Let's try and see if we got the right ones. Okay? 3x times 2x is 6x squared. We got that one right. Then do the outer. That would be a minus 3x. Inner is minus 4x. What does that add to? Minus 7x. Yes, yes, yes. And then the last is plus 2. Yep, we got it. So does this tell you 2 more zeros? What are they? X equal, second, 2 divided by 3, often called 2/3, and x equal 1/2. You say each of those equal to 0 and solve, right? Hey, let's go back and look at this. Does that look like it could be a 1/2 and a 2/3? I bet it is. Okay. So we've just found the other 2 zeros, just noting that. How do we do it? Long division. Now the question is, did we have to do long division? And the answer was no. We could have done it a shorter way for this division, but we haven't gotten there yet. So, they say divide, where did they get this? Divide 6x squared cubed minus 19x squared plus 16x minus 4 by x minus 2. Hey, this is exactly what we just did. Now, one thing they do a little different from me, they shift down. I don't care if you shift down or not, just as long as you get the answer. So they did x minus 2 into 6x, well, x into 6x cubed, 6x squared. Then multiply 6x cubed minus 12x squared. Then change signs and add. They say subtract. I like change signs and add. Make that a minus, that a plus. You get minus 7x squared. Bring down to plus 16x. Divide again. X will go into negative 7x squared. Negative 7x times. Oh, I put it over here, but that's okay. Negative 7x. Multiply negative 7x times x. Negative 7x squared. Negative 7x times negative 2 is plus 14x. Now you subtract or change signs and add. But it's easy to see. Change signs and add, that's going to go out. If you subtract that, 2x. Okay. Bring down the minus 4. X will go into 2x. The plus 2 times. 2 times x is 2x. 2 times negative 2 is negative 4. Equals 0. That confirms what you thought. That x equal 2 was a 0, meaning x minus 2 was a factor. And it gives you the other factor, which is this one. Now, if you can factor that further, which is what? Are they going to do it? Yes, they do. Do they? Yeah, they factor it further. and see that this factors to be these two. Okay, we already knew that x equal 2 was a 0. Now we know that x equal 1/2 is also a 0. Okay. They don't take it any further. Sorry about that. Okay, they just factored it and left it alone. Now, here's what they say next. In this example, you got a remainder of 0 at the end. If you do, you know you factored it. Often, though, longer division will produce a non-zero remainder, and if you get that, you know they're not factors, but you have still done the division. And sometimes that's still helpful. Okay? I don't have my watch out. How are we doing?
9:41.
We got what?
It's 9:41, so 4 minutes.
4 minutes. Okay. Let's see what we can get done in 4 minutes. Okay. So here's another one. If you're dividing x squared plus 3x plus 5 by x plus 1, number one, you know that's not going to go in evenly. Okay, just no way that will work. But you can still divide, and divide x into x squared. You get x, multiply, x times x is x squared, x times 1 is x. Subtract, or change signs and add, and this goes away. This gives you a 2x. Okay? Bring down the plus 5, x will go into 2x, 2 times x is 2x, 2 times 1 is 2. Here you have a remainder of 3. What do you do with it? Remember what I said we would do with the other? What we could do is write the 3 over the divisor, x plus 1. Okay? You could do that if you wanted to. Or you can just say remainder 3. Either one. This sometimes is more helpful. Okay? So in fractional form, if you go back, remember, division is basically a fraction. You're taking your dividend, dividing it by the divisor. That's a dividing line. And what we got for the answer was x plus 2, that was your quotient, plus 3 over that divisor. Okay? So that's written in fractional form, if I don't fall down. Okay? Or even if I do. Okay? And that implies, and here's another way you can write it, that this thing, the dividend, is equal to the divisor times the quotient. Remember how you used to do that? When you were checking, let's go back to this. When you were checking your answers, when you divide, you check it by multiplying. Multiply the quotient by the divisor, and then if you have a remainder, add that to the answer. Well, that's exactly what this is saying. If you have the dividend, it's equal to the quotient. Let's see, which is the quotient? No, the divisor times the quotient plus the remainder. Both of these forms are called the division algorithm. Okay, do we have time to go over that?
We have 1 minute.
1 minute. Okay, let's flash it up here real quickly. Here's a division algorithm. If f of x and d of x are polynomials such that d of x is not 0, you can never divide by 0, then the degree of d is less than or equal to the degree of f, then there exists a unique polynomial q and r such that f of x, what you started with, the big one, higher degree, is equal to d of x times q of x, that's your quotient, plus the remainder of x. Now notice, remainder doesn't just have to be a number, it could be a function of x. Okay? Now, the deal is r of x always has to be a lower degree than d of x. So if that first divisor was a square or cube number, then you could have a remainder that was linear or even square. Okay, for r of x, if r of x is equal to 0, or the degree of r of x is less than the degree of d of x, it has to be. If the remainder is 0, then we say that d of x divides evenly into f of x. In other words, it's a factor of f of x. Have I expended all my energy now? That's the division algorithm. We'll say a little bit about that next time. A little bit more about it. We'll pick up right at the bottom of the page here. Okay. Okay. Now, you might have done enough to get a few problems done. I think you can do number 7 if you'd like, or not. Okay, it should be at Calc Chat. And I think you can do 9 if you'd like. They both are Calc Chat. And then you can do any of the odds 11 through 23. If some of those get too difficult for you, hang on to them. We'll do a few more later. They're all at Calc Chat 19. Good deal. Thank you. Let's see, how many points did you lose on that?
Oh my
Okay. Just kidding.
Bye, have a good day.
You too, thanks. All right, take care. What's that? Yeah. All right.
You say 7, 9, 11, and what about 5?
Okay, wait, just a second. 7, 9, and then any of the odds 11 through 23.
Okay.
Now, some of those you might find may be beyond what we've done, but get started on some of those.
Okay.
Is it going to be another take-home quiz, or is it going to be...
It'll be a take-home quiz. The tests are in class, the quizzes are take-home.
All right, awesome.
Oh, terrible. Okay, I should give the quizzes in class, shouldn't I? Okay. All right. Now, first I'm going to turn off this so it won't be in my eyes. Okay. Next. Okay. Oh, please go here. All right. How is the pace? Is it too fast, too slow, or is it okay? Okay, good. All right. You're not going to leave me a drink? Okay, okay. All right, good deal. Thanks.